several problems which involve the material that we learned in the course. Basically, the things that we learned in the course were representation of rational points on the quadratic. What else? Primitive groups modular prime number, quadratic reciprocity, and Gaussian integers. More or less, that's kind of the really important stuff that we learned. And we learned some really basic stuff, which should be now kind of in background. Some stuff like Riemann-Eagles theorem, Pointer's theorem, so these kind of things should be kind of in background. They're not part of general theory, not part of kind of separate statements which are kind of big theories. They just should be almost common sense. So I want to start with the problem where the notions from this course don't seem to appear, but still they're useful. So the problem is like this. Well, that's not a complete problem, but that's part of the story behind the problem. What is 1 over 7? What I mean is, what is the decimal extension of 1 over 7? And it's not hard to find what it is. You just take 1, you divide it by 7, you get 0 point, then you have 10, which you divide by 7, you get 1, the remainder is 3, then 30 divided by 7 is 4, the remainder is 2, then 20 divided by 7 is 2, the remainder is 6, 60 divided by 7 is 8, the remainder is 4, 40 divided by 7 is 5, the remainder is 5, 50 divided by 7 is 7, the remainder is 1, and then it repeats, because here you have 1, then you have 10, 30, 20, and so on, so it will repeat 1, 4. So the answer is 0 in the period 1, 4, 2, 8, 5, 7. First of all, first thing to notice, there is some period to this expansion. Another thing, well, let's compute with this 2 over 7. To be honest, it's very simple. Yes. Yeah. One of the ways is to multiply this by 2, and well, let's see what we're going to get. 4, 1, 7, 5, 8. Okay, so we got this answer, and what's funny about this is, well, more or less the same digits, except in different order. You have 1, 4, 2, 8, 5, 7. Here you have 2, 5, 7, 2, 8, 5, 7, 1, 4. So it's kind of cyclic permutation. We just take this period, we shift it by 2, and now you got this period. So what is 3 over 7? Yes, it is. So once again, you have the same phenomenon. It's the same digits except permuted cyclically. Yes.
I think it's actually 5, 7, 1, 4, 2, 8.
It's what?
Oh no, sorry, never mind. 3.
So if you start dividing, but
yeah.
let me show a simple reason
No,
why it is this thing. So 3 divided by 7, if you start doing this, well, we have 0 point. 30 divided by 7 is 4, remainder 2. And then you have, well, basically you have the same process as the one here, but it starts with 30. So it is a period, and you have a cyclic permutation here. Well, we can experiment a little bit further. 4 over 7, 5 over 7, 6 over 7. Well, 4 over 7, the computation will start with 40 over 7, which will produce 5. So it is 0.5, and then the period repeats itself. 7, 1, 4, 2, 8. The same here. 5 is one of the digits here, so it is 0.7, 1, 4, 2, 8, 5. And finally, 6 over 7 is 0. So 60, yes, 8. 8, 5, 7, 1, 4, 2. So we have fine phenomenon. We take all these fractions. Oh, the next one, 7 over 7 is not in this form, it's 1. But we have 6 fractions here, and each one of them is just a cyclic permutation of the previous one. I mean, the decimal expansion, the period in the decimal expansion is just cyclic permutation of the other ones. So you have just basically one period, but multiplying it by 1, 2, 3, 4, 5, and 6 makes a permutation. Of course, it is not true when you take an arbitrary number and take 1 over it. Well, 1 over 2 and 1 over 5 are kind of exceptional because they are, well, they don't have infinite expansions, they're just 0.5 and 0.2. But, well, let's say, what is 1 over, I don't know, 11? Yes, so it is exactly like this, 0, 9, 0, 9, and so on. So it is decimal extension with a period of length 2. Well, if you take 2 over 11, so nothing like what we've seen there happens, is 0.18. You can just multiply this by 2. So it's not a cyclic permutation of 0 and 9, not at all. So here you have some phenomenon happening, it is an interesting phenomenon, but it doesn't always happen. So now the question is to characterize those primes for which this phenomenon does happen. What is special about 7? Are there any other primes like this? Well, to be honest, yes there are. We can try to find the next one. Let me check what it was. I think it was 13. 17. So the next one with the same property is 17. For 1 over 17, you will have a period. Its length will be 16. And as you multiply it by different numbers from 1 to 16, you'll get just cyclic permutations of this period as the new periods. So the question is, well, how to think about this phenomenon. This phenomenon, by the way, was discovered first by Gauss when he was just a child in school, and well, he actually made a table of 1 over p for all the primes from 1 to 1000, and he found empirically what is the answer, and well, he had to wait a little bit until he discovered all the number theory to actually prove this result and make it more obvious. So today we do have a theory, the number theory that Gauss didn't have when he was in school. So we can try to understand this phenomenon. So first of all, first question, why is there some period? Why it is always true that if you take, let me keep my number prime, so then prime. And let me make it not equal to 2 and not equal to 5. Those prime numbers, well, they are special in our decimal system. They are divisors of the number 10, which is well, the number of fingers of the hands. And well, they're kind of special for our system. If you take 1 over 5 or 1 over 2, you get just finite expansion. first question, why 1 over p is the logic decimal expansion?
There's only a finite number of reminders you get. What do you divide by?
Okay, so first explanation is like this. You just look at the process. What happens when you divide 1 by 3? You get some result, 0. Then you divide 10 by 3. You get some result, you get some remainder. You take this remainder, multiply it by 10, divide it by p, get some result, get some remainder. But there are only many remainders like this. I mean, all these numbers are between 0 and p minus 1. So eventually, you should get a number which already appeared in the sequence. But this only shows that somehow the periodicity works like this. It's 0 point something, 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 and then a period. So we show this result. Because there are only many options for these results, for these remainders in this process, eventually one of them will repeat. Say this remainder is equal to that one. Well, then our answer is 0 point, this result, and then a period. Why don't we have always a pure period? Why don't we have this part?
So in that sense, like if we want to find a periodic, like for the closer, as in like 10 to be like p minus 1, 1 over 1, 1 over 1 over p. Just like 717. Because of the remainder have to be
So 10 to the power of p minus 1. Okay, I see. So why is it 10 to the power of p minus 1?
because like it means like because if you want like which you want like it's periodic and like to be like something like 7 and 17, so they have to have like 6 numbers. That's true.
Oh, 7 has 6, 17 has 16. Whatever, that's still different. I mean, well, the empirical observation is the period for 1 over 7 was of length 6, the period for 1 over 17 was of length 16. So probably what we just found or guessed is that the period is always going to be of length p minus 1. Well, it's almost right. There is some many here.
Because p is prime, each remainder has a unique predecessor.
Okay.
So
Yes.
Well, you could first say that anything of the form something over 9999999, it will be in that periodic form, so it'll just be whatever's on the top, repeated however many times. And then by Fermat's little theorem, you'll get that 10 to the power of p minus 1 will be congruent to 1 modulo p, which means that 10 to the power of p minus 1 minus 1 will divide p, which means that 1 over p can be written as something over 9999999.
Okay, so these two, well, these two ideas give to the following argument. So first of all, 10 to the power of p minus 1 is congruent to 1 modulo p. That's first observation. This means that this is the rest of 10 to the power of p minus 1. And then, well, with these numbers, k times t. And hence 1 over p is the same as k over k times t. The same as k over k times t is 10 to the power of p minus 1 minus 1. And the next step is well, let's try to actually complete what is 1 over 10 to the power p minus 1 minus 1. And show that for this number you will have periodicity over here, and well, what is this number? I guess it's something maybe 0.001 with the period. And the number of zeros here is p minus 1. So once you multiply by any number k which is smaller than 10 to the power p minus 1 minus 1, you'll get a period with this number k, well, here. Sorry? When p is equal to 1, 1 over 9 is 0.1, so you get okay, so that's a very good explanation. But still there is a question about what is the smallest period we can get. I mean, it could happen that once you multiply this number by k, you get a number which has several repetitions of smaller periods. This large period of p minus 1 is actually a combination of several smaller periods. When this happens. Yes.
Look at the order of 10
Okay. So next observation, let us take any power. So if m is any power of 10 side of 10 to the power of m is equivalent to 1 natural p, then 1 over p is here length n. So basically, we never use the fact that this exponent is exactly p minus 1. It could be any power with the property that 10 to the power m is congruent to 1 natural p. Same argument applies. Okay, in particular, let's take the smallest one. Let's take the order. In particular, 1 over p is a period length order 10 modulo p. But once again, it's still the same question. Why isn't the shortest possible period? So we should find kind of converse state. If we have a period, then period of length k, then 10 to the power k is congruent to 1 modulo p. So we prove that in this direction, if I'm interested in the shortest possible period, I should prove also the opposite direction. So we are still missing a lemma. If 1 over p is the period of length m, then 10 to the power m is congruent to 1 modulo p. So once again, we already have a very good argument for why 1 over p has a period. That's an argument. We have an argument that 1 over p actually has a period of length which is equal to order of 10 modulo p. But we still don't know that this is the shortest possible period. Maybe still, this period still consists of several shorter ones. I mean, this number is definitely the shortest one of those for which we can show this statement, but maybe it's still not the shortest possible overall. So now if we manage to prove that whatever period we have for 1 over p, if its length is m, then 10 to the power m is congruent to 1, then we know then that the shortest one is exactly the order, the smallest power to which you should raise 10 to get 1. So how do we show this statement? Well, let's just play it. Let me call it proof. If 1 over p has a period of length m, or let me call it a1 through am. So suppose that it has a decimal extension like this, and the length of the period is m. So I just rewrote the assumption. Now I want somehow to relate this to the number 10 to the power m. So what should I do? Okay, yes. So one idea is like this. You can take this number and rewrite it as a rational number. You can say that this the number a1 am, like this, I mean just the number whose digits are a1 through am, divided by 10 to the power m, plus the same number divided by 10 to the power 2m, plus, and so on. So this part is just one period, this divided by 10 to the power 2m is the second period, third period, and so on. And then you can take the sum of geometric series. Well, then it is equal to something. Let me make essentially the same computation but in slightly simpler manner. So that's one possible way. Let me make it like this. Let me take this number and multiply it by 10 to the power m. What it does is just, well, shift the decimal point n places to the right. So 10 to the power m times 1 over p is just a1, a2, am dot, and then the whole period once again. So if you take 10 to the power m times 1 over p, and subtract 1 over p, subtract all the stuff which comes after the point, the decimal point, you get an integer. This integer, a1, a2, am. It means that 10 to the power m minus 1 is divisible by p. Hence, p is the divisor of 10 to the power m minus 1. So we started with the problem of, well, what is the period of the decimal extension of 1 over p? And now we got an answer. The period is equal exactly to the multiplicative order of 10 modulo p. Okay, next question. When do we have the phenomenon that we observed in, well, 1 over 7, 2 over 7, 3 over 7, and so on? When all the multiples are just cyclic permutations of the period for 1 over p. So next question. Under what conditions? P over P is period which is cyclic permutation of 1 over P for all from 1 1 over 7, somehow we observed that, well, 2 over 7, 3 over 7, and so on, all the way to 6 over 7, had a period which was just kind of the shift of the period for 1 over 7. In 1 over 7, we had 0.1428 57, 1.42857, and so on. For 2 over 7, we had something like this, 0 point, and then 2, 8, 5, 7, 1, 4, 3, 5, 7, and so on. So the period here, this one, is the same as the period here, except up to the shift. You can find the same period here if you start not right after the decimal point, but a little bit after.
Keep from 1 to 3 months, so that there is no
Yes.
space there.
Say it again. Oh, 6 over 7 is still of the same form. 6 over 7 is 6 divided by 7, 0.8, 5, 7, and so on.
And there is no digit 6 in the period.
That's not what I'm claiming. So I'm not claiming that the period of 1 over p or period of something over p has all the digits in its expansion. No, I'm not claiming this. Not at all. What I am claiming, whatever the period is here, the period for 2 over 7, 3 over 7, all the way up to 6 over 7 is just the same period except, well, shifted. Well, what does it mean that the period for 2 over 7 is a shift of the period for 1 over 7? It means that if you take 1 over 7, multiply it by 100, which means shift the decimal points point two places to the right, you get an integer plus 2 over 7. Let's do the same thing for 1 over b. If period of k over b is the same as period of 1 over b that shifted and place to the right. Then, well, what does it mean? It means that if I take 1 over t multiplied by 10 to the power m, which means I take 1 over p, shift the decimal point m places to the right, I get, well, after the decimal point in this answer, I get the same thing as the period for k over p. So I get an integer plus period of p. And in fact, it works both ways. If this happens, then, well, the period of k over p is the period of 1 over p shifted and places to the right. So I can change the words in here and make the statement stronger. Period of k over p is the same as the period of 1 over p but shifted n places to the right, if and only it's just a equivalent condition. I.e., well, let's rewrite it, 10 to the power m minus k over p is an integer. Or, let's rewrite it once again, 10 to the power k that 10 to the power m minus k is divisible by p. D 10 to the power m is congruent to k modulo p. Okay, so now we just interpreted this condition of taking 1 over p multiplying by k and getting an answer which has the same value as the original one but shifted m places to the right. The condition is like this: 10 to the power m is congruent to k modulo p. So you do get that k over p has the same period as 1 over p, but well, after a cyclic permutation, if k is congruent to some power of 10 modulo p. And well, the exponent here is exactly the number of places you have to shift. Exactly how many times you should shift your period to the right. So now, how would you formulate the condition that for any k over p has the same period as 1 over p but shifted several places to the right? Well, this is the same as saying every k modulo p is some power of 10. So what is a short way to say the same phrase? Well, we just had a definition in our course which says, well, something is true if any residue modulo p is a power of 10. Yes, 10 is a primitive root. So now we have an answer to our question. Answer to the question was once again for what primes p is it true that k over p has the same period as 1 over p but shifted several places to the right? Well, the answer is if and only if any residue modulo p is the power of 10, i.e. well, k over p has the same period as 1 over p shifted several places to the right for any k. If and only if 10 is a primitive root modulo p. So once again, we started with a question which was, well, didn't really come exactly as an exercise from our course. The question was, when do we have this phenomenon similar to the phenomenon we observed with 1 over 7? And now we have an answer which is from our course. It happens exactly when n is a primitive root modulo p. So it happens for 7 because 10 is a primitive root modulo 7. Well, let me combine the first observation about the length of the period, which happened to be order of 10 modulo p, with this observation. So we can write it like this: if and only if, well, order of 10 modulo p is equal to p minus 1. This we know is the same condition as saying that 10 is a primitive root, almost by definition, or not exactly by definition, or without definition. And if and only if 1 over p has a period p minus 1. Because we just know the period of 1 over p is exactly equal, the length of the period is exactly order of 10 modulo p. And now we have a complete answer to the original question, which doesn't use a, well, in its formulation, neither the question nor the answer using anything from our course. The station is like this. The prime p is special in the sense that we observe this phenomenon for this k over p having the same period as 1 over p, blah blah blah. If and only if 1 over p has a period of length p minus 1. Kind of funny theorem, and in between we are using what we learned in the course. We are using order of an element modulo p, we are using the notion of primitive root, we are using the fact that something is a primitive root if and only if every residue is the power of this number, if and only if the order of this number is p minus 1. So we are using some simple stuff from number theory, but we are getting kind of funny situation. I mean, we take 1 over p, let's say 1 over 17. All we have to do to understand whether 17 is a special prime in this sense is just, well, compute this. And 1 over 17 turns out to be 0.05. 0.5 and so on. So 0.5 just repeats. So we just check that the shortest period is exactly of length 16. And I hope this is the right answer here. And then we know that 2 over 17, well, let's compute 2 over 17. We do know that it will have a period which is just like this. We do know how it will start. It's 0.1. Well, is it enough for us to conclude what is the answer? Well, almost. We could start here or here. We have two appearances of 1. So maybe we'll compute the negative digit as well. 2 over 17 or 0.1. 3 over 17 is 2. So 1.
Actually, you can multiply it as the first number.
Oh,
like you got like 10 or like 8 if you times 2 to
yes,
the 8.
30 divided by 7 is 1. Yes, so this number times 2 is 1, approximately 0.1. And then we know that this expansion starts with 1, 1. And then we should have the 7, 6, 4, 7, 0, 5, and so on.
You can also look at all the possible rotations of the period and sort them in ascending order.
Yes, yes. Very good observation. So the observation was, well, for this particular task, maybe it was good, but if I want to find all k over 17, the faster algorithm is just take all the permutations, all the cyclic permutations, and just sort them by how large they are. The smallest is 1 over 17, second smallest is 2 over 17, and so on.
In this case, you would look at all the ones that start with 0, so there's only one choice.
Yes.
Look at all the ones that start with 1.
So there are two choices, so this is 117, 3 over 17 is 0.176, and so on. 4 over 17 should start already with the next one, so it's either 2, 3 or 2, 9. Well, it should be 2, 3. 0.23. Yes. But unfortunately, for primes for which 10 is not a primitive root, for those for which this doesn't happen, we don't have this phenomenon. At least, well, we do have this phenomenon for those residues k which are powers of 10, but not for the others. So, for example, for 1 over 9, 10 is very far from the primitive root. 10 is just conjugate to 1 modulo 9, so for 1 over 9, we don't have any phenomenon like this. Okay, so maybe any questions about this? I want to devote some relatively short amount of time to discussing such a question. Show x to the power 8 minus 16 is root modulo 9. So here's the polynomial x to the power 8 minus 16. And the question is, show that modulo any prime p the congruence x to the power 8 is congruent to 16 modulo p. It does have a solution, but this solution doesn't appear because the original congruence has an integer solution. No, not at all. This congruence in integers is just not solvable. So maybe let's start with the simpler part, why it has no integer solutions. So, solution z, if I try to solve x to 18 minus 16 is equal to 0. So how do we show that it has no integer solutions? Factor. Okay, so what is the factorization?
X to the 4
Okay, so this factor doesn't have any roots because it's always positive. This might have roots, but let's factor it in x squared minus 2x squared plus 1. Once again, these factors can't have roots, but these can, and still x minus also. And this also doesn't have any integer roots. Why? Well, I can factorize it in, well, yes, in reals, x minus square root of 2 times x plus square root of 2, and we do know that these numbers are not integers. And these roots are not integers. Okay, yes, very good, very simple reason. This equation doesn't have any integer solutions. So now next part. I want to show that whatever prime p I fix, I will be able to solve it with the x p y x to the power 8 is equal to 16 modulo p is a solution. Quadratic residues. Why quadratic residues?
But you have the successor is square x. One is twice, 3 times f16. So right now we go down the hierarchy. First the 16 is a quadratic residue of x to the power 4.
Okay, so the first observation, well, yes, maybe it's a good beginning. So this question actually, well, we can rewrite it as x to the power 4 squared is congruent to 16 modulo p, and we know that only two numbers, once you square them, give you 16 modulo p. The quadratic equation y squared is congruent to 16 modulo p has only two solutions, and we just see the solutions, plus and minus 4. So it is the same as x to the fourth is congruent to 4 or negative 4 modulo p. Okay, that's good. We can do the same trick with 4 because 4 is already a square of something. But the question is what will we do with negative 4? Well, so let's extract as much as we can from this trick. So when x to the power 4 is congruent to 4 modulo p has a solution. Well, if and only if x squared is congruent to plus 2 or negative 2 has a solution. If and only if 2 or negative 2 are quadratic residues modulo p. If 2 over p is 1 or negative 2 over p is 1. Well, so in some cases, when this holds or this holds, we will be able to find a solution, in fact, to a simple congruence. Now, this one would actually have to be forces congruent to 4. Kind of stronger statement. Let's check what prime speed do these two cases cover. Well, first case, 2 over p is congruent to 1. The Legendre symbol of 2 over p is congruent is equal to 1. What does it mean? What does it mean about p?
1 or negative 1.
Yes. So this condition is equivalent to p being congruent to 1 or negative 1 modulo a. What about this condition?
That's what it's like. So it's negative. Well, it's like p over 3.
Yes. So here we have, well, we have maybe let's make kind of computation on the side. What is minus 2 over p? It is the same as minus 1 over p minus 2 over p, which is the same as minus 1 to the power of minus 1 over 2 minus 2 over p, which is, well, let me divide several cases according to what is p modulo a. So p is congruent to 1 modulo a, 3, 5, and 3, negative 3, negative 1. So if p is congruent to 1 modulo a, then this is equal to 1, and this is equal to 1. So the answer is 1. If p is congruent to 3 modulo a, then this is negative 1, but then this is also negative 1. So the product is 1. If p is congruent to minus 3 modulo 8, this part is minus 1, but the first part, well, p is minus 3 modulo 8, p minus 1 is minus 4 modulo 8, so p minus 1 divided by 2 is still even, so it is minus 1. So 2 over p is minus 1, yes, minus 1. And finally, when p is congruent to minus 1 modulo 8, this is 1, but this is negative 1. So we get minus 1. So here we have the condition either this holds or p is congruent to 1 or 3 modulo 8. Either this holds or this holds. So we covered more or less all the options except for one. When p is congruent to minus 3 modulo p, neither this holds nor this holds. So we covered all the options besides when p is congruent to minus 3 modulo 8. So the question minus 3 modulo A.
For negative 4, it's a quadratic form.
Oh, a quadratic residue, well, we have to show that it's not just a quadratic residue, that it is fourth power of something.
Sure.
So let me write this down. So we decided that when P is congruent to minus 3 modulo A, this equation, x to the fourth is congruent to 4 modulo P, it has no solution. Well, we had if and only if conditions all the way through, so this congruence has no solutions. For P which is congruent to minus 3 modulo A, we have to prove x to the power 4 is congruent to minus 4 modulo P has a solution. Okay, how do I approach this question?
You already know P is negative 3 mod.
Yes.
Well, actually, this we would have, that means like x to the fourth modulo 4 of P without 2 quadratic number groups. That means 2 quadratic number groups multiplied by quadratic groups.
Say once again, so by P of this form, we go that 2 is a quadratic non-residue and minus 1 is a quadratic. Minus 1 is a quadratic residue. Right?
Wait, that means like in P pound with minus 3 is 8.
Yes.
That means for the ball 1, also for the ball 1.
Yes.
So it's 2 and minus 2.
Yes.
Is quadratic number groups.
Yes.
That means minus negative 4 is quadratic residues.
Oh, I see what you mean. Yes. Okay, that might be a good first step. Let's see whether we can get a solution from this. So for P which is congruent to minus 3 modulo A, we decided that both 2 over P is minus 1 and minus 2 over P is minus 1. This means that minus 4 over P is actually 1. Okay, that's a good observation. It means y squared is congruent to negative 4 modulo P has a solution. Okay, so y squared is congruent to minus 4 has a solution. Well, it has two solutions, y and minus y. If you fix one, y, the other one is minus y. So y and minus y are the solutions. But we still have to show that y can be interpreted as x squared, or maybe minus y, it's x squared. So still we have to show that either x squared is congruent to y modulo P, or x squared is congruent to minus y modulo P has a solution. Okay, that's very good. So how do we show this thing?
So that right? This turns out to find quadratic residue, like minus 1 equals 1, or minus y is equals to
Yes. E. had this condition is the same, because minus y over p is minus 1 over p times y over p, and minus 1 over such a prime. This prime is congruent to 1 modulo 4, so p 1 over p is equal to 1. Well, because minus y over p is minus 1 over p times y over p, which is the same as y over p. This p is congruent to 1 modulo 4. We assume that p is minus 3 modulo 8, it means it's minus 3 modulo 4, it means it's 1 modulo 4. So we still have to show that y is a quadratic residue modulo p. How can we show this? Well, we know that y squared is congruent to negative 4. And we know that p is 8k minus 3. Any ideas? Now, what tools do we have to show that something is a quadratic residue? Well, we have a complicated tool called quadratic reciprocity, but it's hard to apply it here because we don't really know what y is. We only know what y squared is. So quadratic reciprocity is basically not a good idea here. What other tools do we have? Direct means write the formula and show that b squared is congruent to y. Once again, it's complicated because well, you don't know that much about y. You know only that squared is minus 4. So I'm not sure that it will work because I prepared a different solution, but I think we can try to use Euler's criteria. Y over p is congruent to y to the power p minus 1 over 2. So let's try to see whether it is the solution. What is y to the power p minus 1 over 2? It's y to the power p minus 1 is 8k minus 4, so it is 4k minus 2. Okay. At least I can transform it. It's y squared to the power 2k minus 1. So it is minus 4 to the power 2k minus 1. So we have to show that this number is congruent to 1 modulo such modulo p. Okay, so let's take a break and I'll see whether we can finish this and find a solution along these lines. If I don't find a solution along these lines, I'll show a different one. Wow. So it's just a 10 minutes break.